So nice when everything works. Okay. So let me do a sound check. Great, thanks. Good. Okay, so maybe we should begin. So last time we were talking about strong linkage for Verma modules, not Verma modules, but for biomodules and induced modules. So let's go back to the notion of strong linkage. All right, so there are certain players going on here. So G is a semi-simple algebraic group. And K is an algebraically closed field of characteristic P. And so what was important in the representation theory, it's the affine biology. And last time we actually stated strong linkage. So here's a, let me call this strong linkage version 1. Okay. So this is strong linkage. Let me call that number 1. All right. So it says the following. So it says that if I have a composition factor inside an induced module, or equivalently a vial module, so I have a non-zero composition factor inside of this thing, then we know that U is strongly linked to lambda. So what that means, I won't write it out again, but it just means that you have a bunch of simple reflections in the affine vial group so that you can get from this one to this one in a way where you don't increase in terms of the order. Okay. So we saw that you have to have this chain where you go from one alcove to the next alcove, but everything is less than before. Now, you may ask yourself, is there a version for the strong linkage which involves higher cohomologies? And the answer is yes. So let's call this strong linkage 2. So let me state strong linkage 2. So let lambda just be a weight, okay? But the weight has a condition. So it's lambda plus rho alpha check is bigger than or equal to 0 for all. Okay, it's enough to just do all simple roots. All right, so it basically lies in that when you shift the hyperplanes down to minus rho, it lies in sort of the chamber containing the dominant chamber. Okay. All right. Now, suppose that mu is in xt plus. So if hi w dot lambda, because I used to use the dot action, of L mu is not equal to 0. Okay, so I here is bigger than root 2 0. For some, okay, so then the same statements. Okay, so it says something about what happens with the higher sheaf cohomology models. You sort of go around under the dot action. And notice that there's no upper bound on this. So it's not like Bott-Barrel-Big. So it actually tells you something a little bit more than with Bott-Barrel-Big. Okay, questions on this? All right, now there's a history to this. And so let me give you a little history to these two results. Okay, so first of all, Verma conjectured strong linkage 1 back in 1971. So Verma conjectured strong linkage. I'll call it Marcel. And it was back to 1971. Okay. And then the first kind of result in this area actually happened in characteristic P. This is even before like BGG category L. And so Humphreys in a paper in 1971, proved not strong linkage, but just linkage under the affine boundary for the modules, the ZR lambdas. Okay, so remember these were like induction from VR to GR lambda. So these are the baby Verma modules. Okay, he actually proved it just for G1, but same kind of result holds. Okay, so 3. So this strong linkage 2 this was proved by Anderson. Henning Anderson in 1980. And the proof is actually in Janssen's algebraic groups book. You can actually read the details if you want to read the details of this. Okay, and strong linkage 2 implies strong linkage 1. Okay. Now, there turn out to be connections between strong linkage for Roma modules or induced modules and strong linkage for these baby Roma modules. So Janssen actually proved that if you have strong linkage for the induced modules, it implies a strong linkage for the Roma modules. So Janssen proved strong linkage for the ZRs implies a strong linkage for the Verma modules, or equivalently the induced modules. And then finally, Doty in 1987, he actually gave a proof of strong linkage. So if you have strong linkage of these modules, so strong linkage for, this doesn't mean SL, just strong linkage for the ZR lambdas as what are called GRT modules. Implies the strong linkage for the Verma module. So Steve's paper appears in the American Journal of Math. It's a really beautiful paper. He said that he told me this story one time that he was riding his bike, and he thought about this idea of riding his bike. Luckily, he didn't crash his bike or anything. He went home, he wrote it up over the weekend. He got a very nice paper out of it. All right, great. Now, I just want to mention one more thing. So this is related to strong linkage 1. So this is an application. So let me just leave strong linkage 1 up here. So here's an application. So it says the following. So let lambda and u be in x dan g. Oops, sorry about this. So no. So let these be dominant weights. Okay. So so then if any x between, so let's say that I have an extension. It could be x1, it could be x2, it could be x to 100. And so suppose this is non-zero. All right. So for some n bigger than 0. Okay, so then this implies that lambda is in the same orbit as mu. Okay. All right, so we know this for n equals 0. So for n equals 0, this is very easy because x is just Hom. Right? The only time the Hom is non-zero is when lambda is equal to mu. So this condition is obvious if lambda is equal to mu. Just take the identity element, right? Okay, so this is okay. So for n equals 1, if this is non-zero, well, we know what happens in this situation. Either L lambda is in the second layer of H0 mu, or L mu is in the second layer of H0 lambda. So this implies that either L lambda is in the second Sockle layer of H0 mu, or vice versa. Yeah, it's one or the other. But in any case, in one case or the other, lambda is L lambda is a composition factor of H0 mu. So you can use strong linkage, or vice versa, right? So that means that lambda WP orbit. They're in the same WP orbit under the dot action. Okay, now you can generalize this by just doing the following. So how do you compute X? Well, to compute X, so what you can do is you can take an injective resolution of all mu. So I can take an injective resolution here. So this guy goes in here. This is an injective resolution. Now, the way you can construct the injective resolution is, what are you doing? You're sort of looking at the first one, right? And this is going to be what? This is going to be the injective. If you want to do minimal, if you want to take the minimal one, you can just take the injective whole of mu, right? Now, let's use reciprocity. So if I use reciprocity, we know that this has these factors in it, right? Okay. And now we use strong linkage, right? Because here, in order to have a composition factor, sigma and mu have to be in the same WP orbit, right? So if this is non-zero, this implies that sigma is in the same WP orbit of mu. Okay, so that means that any of the factors inside of I mu have to be H0 mu's, which are linked, right? But all the composition factors are going to be linked for this one here. So this means that if I mu, if I take a composition factor like this implies that gamma has to be. Okay. All right. So that means when I take the quotient of this by this, it's going to have composition factors which are linked to mu, right? So this next one over here has to consist of direct sums of i's. So implies I1 has to be like I of gamma 1 plus 2. And all of these here have to be linked. Okay. All right. So then you continue this on, continue this process on, right? So all the composition factors in the minimal resolution have to be linked to mu. Right. So that means that, so what is this going to be? It's going to be a subquotient of the Hom. Right. So X tan this is a kernel mod image, right? Okay. All the composition factors here have to be linked to mu. So if this is non-zero, this has to be non-zero too. So that means that mu has to be, lambda has to be linked to mu too. So if this is non-zero, and if this is non-zero, so lambda has to be. Because all the composition factors in IN are linked to mu too. So we're using the reciprocity, which is going to be also strong linkage to actually show this.
Reciprocity.
This one up here. This is the Brown reciprocity.
What are those? What is I gammas again?
I gammas.
Are that supposed to be L?
Yeah. So what you do is you take. This is a good question. So you take this mod this, okay, and then in order to compute this, you look at the socle of this mod this, right, and that'll give you the injective hole. Okay, and so these mu's are the L gamma i's are the socle of this over this.
Okay, but so I1 decomposes as the sum of injective holes corresponding
Yes.
to those lines. So
That's right.
results. Yeah.
That's right. It's this thing that you do, like in your Paul. This came up too as an essential homomorphism. It's the same. It's exactly the same thing. That okay. Other questions? Okay, so I think I have full attendance today, so I'm going to take advantage of this. I'm going to take a little break. I'll take a little class picture here. I think everybody's here, right? Yes. Everyone's like that. All right.
So it's this last WP not the dot action.
Yeah. All right, let's see here. Everyone smile. Let me see. Give me a peace sign if you want. All right, good. Yeah, let me try another one. Okay, one more. Hopefully that'll be enough. Okay, great, thanks. Any questions about the attendance or now will be dismissed. Okay. All right. Okay, good. So this is good. This ends the strong linkage section. So now we're going to move on to the notion of translation. Okay. All right, so maybe some of you saw this in the DGG category O class. So let me kind of give you kind of an idea if you've seen this a little bit before. All right. So this is for the Lie algebra, the SL3C. All right, so what I've done is I've taken the hyperplanes and I've shifted them down to minus rho. And here's 0 inside of this alcove. All right, so in this picture, there's a notion of alcoves and walls. Okay, so the alcove looks something like this. Okay. And then the idea is there are walls. And so the walls are here. This is the wall. And so you have these blocks for category O. So you have the principal block. And it turns out that if I take another weight, which is also in the alcove too. So let's call this lambda. And here lambda is called a regular weight. So a regular weight is a weight which just doesn't occur on a wall. And you can look at the block corresponding to the regular weight. And so does anyone know what the relationship is between the principal block and a block corresponding to the regular weight?
It should be the same. Or,
Well, same in what sense?
do you mean if they're in the same alcove like there?
Yes.
Then aren't they not isomorphic?
Well, what do you mean by isomorphic?
Maybe I don't know that.
No, I think you do.
For equivalence categories?
Yes, it's Murray equivalence, right? See, the thing is, the dimensions of the symbols may not be the same, right? But there's a Murray equivalence.
Okay.
Right? So there's an equivalence. So that's a theorem. Okay. Now, what could happen is you can look at weights which are on a wall. So mu. So mu is called a singular weight. And so these translation functors allow you to translate from an alcove, block in an alcove, to a block corresponding to weight on the wall. So I can translate B lambda. And so I want to define these translation functors. And then I'm going to translate off the wall. So these are what are called the translation functors. I haven't defined them yet. So I guess the first few, certainly Janssen was one of the first ones to kind of study these. And it turns out that by going to and from codimension one walls is very important for the theory. Okay. It sort of involves, once you actually know something about this process of translation, then it turns out to be equivalent, let's say, to the causalist conjectures. All right, so this is a category L. All right, so now what do you think we do for algebraic groups? Well, we kind of want to look at the same picture, right? So let's say G is a semi-simple algebraic group. So what I'll do is I'll look at the same picture over here. But remember, this time we just can't look at this, just this, this big sort of chamber over here. It gets subdivided by using affine hyperplanes. So I have something which looks like this, and I have something which looks like that. And the picture sort of goes on. Okay, goes on forever. All right, so what is CZ bar? Well, CZ bar over here is this alcove. So we can only take weights which are down here. So maybe we have weights which are like this lambda u. Now we can also have mu on this top alcove too. That's a possibility also. So we're going to first limit ourselves to the things inside of CZ bar. So you're down in whatever. Maybe some people call it the sleazy bar, right? You only take weights in the sleazy bar. Doesn't sound good. Okay, so that's what we're going to do. Now, before we do this, I want to actually talk about blocks. So we kind of know what blocks look like here. If you just take the WP orbits on this, you get the blocks. Now, it's a little bit more subtle for algebraic groups. So let me talk about blocks first. In this context. All right, so the way you define blocks, now we did define it using idempotencies for finite dimensional algebras, but there's another way to do it too. So we say that two simple modules are in same block if we have a bunch of simple modules, P1, P2, Pn, such that S is equal to T1, and then I have T2 to Tn, T. So two simple modules, S and T, on the same block. Okay, so if and only if I have that x1 ti plus 1 not equal to 0. Okay, so here's the TJs are simple one. So basically, in order to be S and T for them to be in the same block, I need a chain of simple modules where the X are all non-zero from one to the other. Okay. And then what you do is you complete this to an equivalence like, they should. So you complete this. To equivalence relation. All right, now, the nice thing is when you take a module and you look at the indecomposable components, then you could actually decompose it in terms of modules in a certain block. Okay, so I will just state this. Yes, I'll just state it as a lemma. The proof's in the books. Okay, so here's the lemma. Okay. So let M and M prime be rational G module. Okay. So then one, I could say rational H module. All right, so then M is equal to direct sum. I'll explain the notation in a second. B and A should be MB. Okay. So basically what you're taking is, you're just sort of taking all the modules which have composition factors in that block as MB. Okay. So where MB is equal to the sum of all submodules of M, M prime. You just take the direct sum of all submodules where M prime has composition factors. Yeah. Okay, so I put this equivalence relation on simple modules. So just kind of locating all the simple modules in the block B, and then you take a sum of all these things inside of MB, which have those composition. That's all you're doing. So basically, you're taking a module and sort of it sort of splits up into receptacles, and so you just sort of stick the stuff in various receptacles in certain places depending on what block it's in. Okay, so 2. If I take the X of M and M prime, okay, so then it's a product of all B and B of H. Okay, so B of H are all the blocks of H. And you could just take so these indecomposable components, they only speak to each other if they're in the same block. If they're in different blocks, there can't be any X between them because of the reason that I gave earlier in terms of that argument involving injective resolutions. Okay. So X die should be an H. Okay. Of MB M. They only speak to each other if they're in the same block. Okay, any questions on this? Okay, so I have to retake my picture because I think now everybody's serious. Sorry about that. I just wanted to get a picture of it. try to cross present. All right, one more time. Okay. East side. Okay, great. One more. Okay, great. All right. Well, that should be enough for this semester. Okay, good. All right, now the question is for a semi-simple algebraic group, what are the blocks? So let me just keep this picture up here, and I'll sort of do something over it. So this was actually determined by Donkin. It's not exactly the relationship that you think about in terms of the strong linkage. There's a little bit more to it. So let me say this. So let L lambda be an irreducible representation, and B lambda be the G block containing L lambda. Okay, so you just look at all things which have extensions with simple modules from L lambda to the other simple modules. Okay. So we have of course that B lambda is a block of G. Okay. And so one thing obvious is if I look at so I'm going to be a little sloppy here. And so B lambda contains all the irreducibles L mu, which are in the same block as L lambda. But what I'll do is I'll just think of them as being weights. Okay. So what are the weights in here? So let me just put one of the little quotes, okay? So not the irreducibles, but the weights inside of here. Well, clearly they have to be dominant. We know that. And what else do we know? Well, we know that the weights have to be linked to lambda under the affine biology. And that's by strong linkage. Now, it turns out that the equality may not be true. It's almost true, but it's not quite true. So let me state a theorem. I'll just state the general theorem. So there's a result by Steve Donkin, which is a sub-theorem of this theorem. I think it's due to him too, so I'll give him credit. So theorem. Let's say it's due to Donkin. I think it's right. Good. So let lambda be a dominant weight, and R the largest what? Integer. Such that C to the R divides lambda plus rho off the check. Yeah, I guess it's for some that alpha, right? Let me see what Donkin's result is. No, I think it's for all alpha. Okay, so for all alpha in phi. Okay, so then B lambda. So the block here I'll put this in quotes. The weights of the block are in, let's see, WPR. So I think this involves the PDDR vial group. Intersection next. Okay, so let me say what this is. So WPR is the vial group semi-direct product of PDDR times. Okay. So just not R equals 1. You have to take higher R's. Okay, any questions on this? So notice that if you have singularities, if you're on walls, then your blocks are sort of linked by, other things than just only the affine block. Well, you have to take a variant of the affine block. Okay, so now let's go and try to define the translation functors. All right, so I'm going to start with the setup over here. So we have this setup. And so I have to define certain functors. So let V be a G model. And now what I want to do is I want to look at all like factors which are linked to lambda. So let's say lambda is in x of t. So set the projection of V to be equal to the sum of submodules with comp factors L mu. So mu is dominant and mu is linked to lambda. Okay, so lambda can be any weight you want. You just look at the WP orbit and then you look at the dominant things in the WP orbit and you see which ones apply it. Okay, great. So here are some properties. So so I need to let Z be something. Okay, I'll let that be something here. So what you can do is you can sort of look at representatives of WP orbits. Okay. So when you take the representative of WP orbits, then this V is a direct sum of these projections. So Z are representatives of the WP orbits. All right, so I guess, so, you can just see that you take this one, this one, this one, this one, this one. You know what I'm saying. You just take the WP orbits and then you take the next one and the next one. So on. All right. Now, again, because of this sort of block phenomenon, different PRs they don't talk to each other. So if I take X to V and V prime, the only things that talk to each other are the same PRs. So this is a product of lambda and Z of X I of G PR lambda PR lambda.
There's no restriction on lambda to be regular here, right? This works even if it's singular.
No, because the thing is, even if you're singular, right, you're going to capture all the dominant ones in the orbit.
Right.
Okay. So it's independent of which representative you get. Good. Okay, so these projection functors are nice. They just take your module and they sort of basically just split things up into blocks. And the last thing is that this is a projection functor, so it's exact. So PR lambda blank is an exact function. Okay. All right, so let's do some examples. We'll see how this works. So if I take PR of mu, right? So you can tell me what happens here. What if lambda and mu are not in the same WP orbit?
Zero.
You get zero, right? So certainly zero if lambda is not in the same WP orbit as mu. What if they're in the same WP orbit? What do you get?
Just L of mu.
Just a little mu. So that's a nice, easy computation. And similarly, by strong linkage, if I take HI of mu, and of course it's zero if, well, let me just say it's the same module. So these are all, if mu is in the WP orbit of lambda. Okay, zero otherwise. Okay, so these PR lambdas are not so hard to compute. Okay. All right, so let's picture on the board. So let me remind you what CZ bar was. And now I define the translation factors. So CZ bar is equal to the set of all lambda and xt, where 0 is less than or equal to lambda plus rho beta check less than or equal to p for all beta and 5 plus. Okay, I just wrote the definition of CZ bar. Yeah. Okay. Now, whenever you have two things down here, I can take the difference, and it's a weight. So for every lambda mu in CZ bar, only consider the difference mu minus lambda, which is just a weight. Okay, it may not be dominant. But if you take a weight, I can always conjugate it to a unique dominant weight. Okay? So there exists a new prime, which is dominant, and it's also in the W orbit. Now, this is under the ordinary action, not the dot action. Okay, just the ordinary action. So you look at the difference, you conjugate it back into the dominant region, and that gives you a new prime. And so here's the definition of the translation. Okay, so definition. if I take translation from mu, so I'm going to take something from PR of lambda to PR of nu. Okay. So I'm going to take an arbitrary module, and here's how you construct it. I got to leave enough room. Okay. So the first thing you do is you take your V and you project it to lambda. That's the first thing you do. Right? And then you're given lambda v over here. So you take this weight, it's dominant. So I can tensor this whole thing by the irreducible corresponding denominator. Okay. And then I project onto mu. That's the definition. Okay, so I project first to lambda, tensor it by this irreducible representation, and then project down to mu. Okay, so so this functor T lambda mu, it goes from, well, it's better than just G modules. It's G modules where PR lambda is equal, V is equal to V to G modules. It kills all the other stuff. Okay, so it's a functor which goes basically from G modules to G modules. And T lambda mu is an exact it's exact because PR lambda is exact. We're tensoring over K, which is exact. And then again, we compose with an exact functor. So it's an exact functor. Okay. All right. So I just have a couple more minutes. And so let me just preview what we're going to do next time. So the next time, what we're going to do is we're going to look at these functors and show the following. So if you take T, so if you sort of go from the block here for lambda, let's say to the block for mu, right? And if you can also go from the block for mu to the block for lambda. So this, these, and these functors. There's a relationship. So they're adjoint. Okay, so we'll actually prove that they're adjoint functors in one another. This will be a very important property because we'll be able to sort of swap, one functor to the other side of the extra Hahn using the adjointness. Okay, that'll give us some information. And the beautiful thing about these functors is that if your two weights are inside the outcome, and this happens in category O2, the definition is exactly the same in category O. There's no difference. It's the exact same definition. So if you're inside an outcome, then these produce the categorical products between the blocks. Okay, so that's kind of how it works. These are the exact functors that produce the categorical. All right, so then we'll actually prove that later. Okay, any questions on this? Questions? Okay, so we will see you on Friday.